Let's finally bring the natural log function into the natural log lesson, shall we? Remember, we have equivalent exponential forms to our logarithmic functions. And so if y equals the natural log of x, then its equivalent exponential form is e to the y equals x. And we want to use this equivalent form because when we want the derivative with respect to x of the natural log of x, we're going to use this form because now we know the derivative of e to the x. And this is the explicit function. And when we put it in its equivalent exponential form, this becomes an implicit function. So we're going to implicitly differentiate. So we want the derivative with respect to x of e to the y, and that must equal the derivative with respect to x of x. So I've taken the derivative, done the same math operation on both sides of the equal sign here. So this is a chain rule. It is the derivative of the outside, not changing the inside, times the derivative of what's inside. And remember, the derivative of y with respect to x is dy dx. And the derivative with respect to x of x is just simply 1. In implicit differentiation, the next step is that we solve, using good algebra, we solve for dy dx. So it has to be true that dy dx is 1 over e to the y. Now we want the derivative with respect to x of the natural log of x. We don't want it in terms of y, we want it in terms of x. So we need to find some way to write e to the y in terms of x. Well, here's that way right here. We started out with e to the y equals x. So everywhere we see e to the y, we are able to write x instead. So there we have it. I know it's a long time getting here, but the derivative with respect to x of the natural log of x is 1 over x. I want again for you to put it in your notes using the chain rule. Let's incorporate the chain rule. And remember, here is the outside. And here is the inside, just like we saw with e to the u. So the outside is the natural log of, whatever we feed it. The inside is that expression that we fed the natural log function. And so when we verbalize, just like we always have, the derivative of the outside is 1 over, right? 1 over something. So it's the derivative of the outside, not changing the inside, there's the inside, times the derivative of what's inside. So there is the derivative for the natural log of u incorporating the chain rule. Let's do a quick example here. If y equals the natural log of the expression x times the square root of the quantity x squared plus 1, then dy dx equals what? So here is a function, the natural log of u, right? And here u is that expression inside, and we want dy dx. So dy dx is the derivative of the outside. That's 1 over. There's the derivative of the outside. Not changing the inside. The inside is x times the square root of the quantity x squared plus 1. Now, times the derivative of what's inside. Here's du dx. So now I'm just down to what's inside, which is a product. So that's 1 d2, and this is information we know how to do. We've been doing this for a long time, right? There's 1 d2 plus 2 d1. So there is the chain rule. Now this is a multiple choice question, so we're going to have to do some algebra to clean it up, which is probably going to take far more time than the calculus step did. Let's work in the numerator here because recognize that 1 over this means that this just becomes the denominator of this fraction when we multiply it through. So let's quickly rewrite it that way. And so if we try to clean it up so we can match one of those choices, this cleans up to 2x squared times 1/2. So those things cancel. I dropped my negative 1/2, didn't I? Yeah, so 1d2, 1/2 pops down front, reduce the power by 1. So this becomes x squared plus 1 to the negative 1/2. That x and that x are x squared, plus x squared plus 1 to the positive 1/2, all over x times the quantity x squared plus 1 to the positive 1/2. Now, I tell you what we could do. Let's see if we can get these two terms put together. This is actually x squared over the square root of x squared plus 1 plus the square root of x squared plus 1 over x times the square root of x squared plus 1. So it looks pretty ugly, looks nothing like any of those choices up there. So let's get a common denominator in the numerator, and maybe we can get a fraction over a fraction and get it cleaned up. So in the numerator, we're not working in the denominator of our original fraction yet. We're just working here. Our common denominator is going to be the square root of x squared plus 1. Now this numerator is unchanged. That's x squared. But this numerator, we've got to multiply this by a well-chosen one of that root over that root. And that's what would give us this as the denominator of this fraction. So this is actually x squared plus 1, because it's the square root times the square root. So now we do have 2x squared plus 1 over the square root of x squared plus 1. We can flip the bottom and multiply straight across, and here's what we get, x squared plus 1. Now we're going to get x times the quantity x squared plus 1 on the bottom, and 2x squared plus 1 on the top. And there we are. That's choice D. All right, so there's an example using the chain rule for the derivative of natural log. Let's talk really quickly about what we remember about the parent graph, the parent function of y equals natural log of x. Remember that the domain for natural log is all positive real number values. Remember, that's the range for e to the x, and those are inverse functions. The range for the natural log function is all reals. You can see everything from negative infinity to positive infinity along the y-axis. We know that we only have one on the parent function. We only have one root, or 1, 0. That's the point 1, 0. And so there are some things that we know about the parent function. It's always increasing. It is 1 to 1. It does have an inverse. Those kinds of things we know for certain. From a calculus standpoint, let's talk about what we know about f of x equals natural log of x. So moving beyond our pre-calculus work, let's look at what calculus tells us. If f of x is this function natural log of x, what can we say is always true about the first derivative, f prime of x? Do we notice that the slopes everywhere are going to be positive? And that's true because the natural log function is a strictly increasing function, meaning it increases everywhere, so its first derivative has to be positive everywhere. Let's look at the second derivative. What's true about the second derivative of the parent function? Notice that this function, natural log, is always concave down. So the second derivative is always negative. Additionally, when it comes to calculus, let's look at these limits. Let's look at the limit at infinity, and let's look at this one-sided limit. So as our inputs head down toward the positive end, toward x tending toward positive infinity, what are the outputs of this function doing? Well, they're growing very slowly, but they're still continuing to grow. And given enough time, and infinity has a lot of time in it, it is true that the outputs of that function will go to infinity as the inputs get near infinity. So there's the limit. As x approaches infinity of this function, the outputs do go to positive infinity. So let's look at what happens as we approach an x value of 0 from the right. That's what's happening on the right side of this y-axis, right? Well, we can tell what the outputs are doing, and remember that's what the limit asks us. The outputs are headed toward negative infinity. Now, all of those calculus attributes that we just covered, first derivative positive, second derivative negative, outputs for large inputs going to infinity, outputs for inputs near but to the right of 0 going to negative infinity. Those things you need to be able to call up immediately concerning the natural log function. Remember that our definite integral, where we accumulate area in the plane, gives us our antiderivative function. So the geometric meaning, the definition for the natural log of x, is to accumulate the area in the plane underneath the function 1 over x, starting at 1 and stopping whenever they tell us to. So for instance, the natural log of 3 is the accumulated area in the plane from 1 up to 3 underneath the function 1 over x dx. And it makes sense that if the derivative with respect to x of the natural log of x is 1 over x, it should make sense that the antiderivative for 1 over x should be the function, the natural log of x. All right? Okay, let's work some examples here. Here, when we know the antiderivative, and let's say it's 1 over u du, and we know that that is the natural log of u plus c. Now, if we have something being operated on, and the only operation that we can see is that it has been put into the denominator of a fraction raised to a power of 1. Now, this is not equivalent to 1 over u squared du. That is something we've been able to do for a while. What we haven't been able to do is this. Why? Because the power rule, if we use the power rule, it's 1 over n plus 1, u to the n plus 1. Notice a problem there? Yeah. Hold on. We don't have division by 0. So the power rule is not used when we're talking about the antiderivative of 1 over u. That's natural log of u. So when we have something down here that's being operated on that's raised to a power of 1, we could choose that to be u. Again, using our process, we ignore what's here and we find the derivative. That's 0 plus the cosine of theta, d theta. And if we can completely rewrite that in terms of u and du, then it's a u substitution problem. And the antiderivative here is the natural log of u plus c. And so for us, when we back substitute back into our original variable, which here for us is theta, there is the antiderivative function for this function. All right, let's work another example. Something is being operated on. It's been put into the denominator of a fraction with a power of 1. Let's choose that to be u. du is 3 dx. Now I'm going to pop my 5 out front, and I'm off on just 1 over the quantity 3x plus 1. I'm off by 1/3, right? So this becomes 5 times 1/3 of 1 over u du. So the antiderivative in terms of u is 5/3 times the natural log of u plus c. I'm going to pick that up. 5/3 times the natural log, u is 3x plus 1, and I have a definite integral now. Remember, there's our process. So we have 5/3 times the natural log, that's 3 times 4 is 12, plus 1 is 13, minus 5/3 times the natural log of 1, and we know the natural log of 1 is 0, so there's our answer. I'm going to stop this. We'll do the last and final video, and we'll talk about using logarithmic properties to evaluate limits, and that should finish up this lesson.